Rate equation reaction. So to calculate how fast our reaction is going, one way of doing that, you could do a change in concentration over the change in time. Now the average rate is going to be negative if the reactants are disappearing. Remember, the reactants are the stuff that's on the left. It's going to be a positive rate if the products are appearing, and remember, products are on the right. So sometimes you'll actually give the negative or positive value, especially if you don't subtract the correct way or find the difference exactly the right direction. So here's an example. We have hydrogen reacting with chlorine to form hydrochloric acid. Calculate the average reaction rate for hydrogen. Well, if we look at our change in time, the change in time is the same for all of our substances. The change is going to be 4 seconds because we started at 0 and we're stopping at 4. So if I want to look at my hydrogen, I'm going from 0.03 to 0.02. So I'm decreasing by 0.01. And since I'm decreasing the concentration, it would be a negative change. So then divided by 4 seconds gives me a rate of negative 0.0025 molar over seconds. Again, it's negative because the hydrogen is disappearing as a reactant. Now chlorine, if you look at chlorine, even though it's a different concentration at the start and the beginning, or the start and the end, it still has the same change. And that's interesting to note. If you look at their coefficients, chlorine and hydrogen have the same coefficient, so their rates should be the same. And in fact, we do get the same rate. Again, it's negative because it's a reactant that's disappearing. For HCl, since it's a product, we're actually gaining 0.02 molar, so that's going to be a positive value. You don't have to show the positive if you don't want to for the rate. Notice that the rate is double that of hydrogen and chlorine, and if you look at the coefficients, it's a 1 to 2 ratio, so hydrochloric acid should be twice or be being produced twice as fast as the hydrogen and the chlorine are being consumed. Rate law helps to explain how the change in concentration is related to the speed. We only deal with reactants, we don't deal with products here. So if we look at this generic reaction, our rate law would be rate equals K. It always starts off with rate equals K. Don't leave that off. Then you have your reactant in brackets to represent concentration raised to the value of N. N is the order that you have to figure out based on data. K is the rate law constant. So K is always going to be the same no matter what set of data we're looking at. So here we have a problem. We don't really need to know what the products are because products are not involved in the rate law. And what we want to do is we want to figure out the order for each reactant and then write the rate law. So to figure out the order, we need one reactant to change while the other one remains constant so that we know how changing the concentration affects the rate. So if we look at our sets of data, and if we think about reactant A changes if we look at the first set of data and the last set of data. And B stays the same, so that we can look at how changing the concentration of A changes the rate. Well, A's concentration is doubling, raised to some N value, and my rate is also doubling. So that means N is 1. So the order for reactant A is first order. Now if I look at B, I want to look at the first two sets of data because B is changing while A stays the same. Again, B is doubling, so we'll say 2 to the nth. And if I look at my rate is staying the same, so that is a value of 1. That means it's 0 order with respect to B. So when I write my rate law, I want to make sure I start off with rate equals K, and then we would say A to the first and B to 0. Now we don't have to include 1 because ones are understood. Anything raised to 0 is going to give us the value of 1, so B isn't actually doing anything. So we could write this as rate is equal to K times A. So what's the overall order? To figure out the overall order, all you have to do is add together your n's. So we're going to say 1 plus 0 gives us an overall order of 1. Now what's the value of K? We're going to take one set of data and plug it into our rate law. So if we take the first set of data here and we plug it into our rate law, the rate is 0.32 molar per second. That equals K times A, which is 1.5 molar, and it's to the first. So all we have to do here is divide by 1.5. And we get a value of 0.21. Molarity cancels, and I'm left with 1 over seconds, so we'll say 1 over seconds. You could also write that as 0.21 s to the negative 1. Alright, if we look at another example here, we want hydrogen to be changing while nitrogen monoxide stays the same or constant. So let's look at the first set of data. So hydrogen is being cut in half, so we can say 0.5 raised to the n is equal to, and my rate is also being cut in half, so that means n is equal to 1. So it's first order with respect to hydrogen. If we look at nitrogen monoxide, we would want to compare the first and the last set of data. So here nitrogen monoxide is quadrupling, or being multiplied by 4, so 4 raised to the n is equal to, and if I look at my rate is also quadrupling, so that would be to the 4th, so n would still be 1. So to write the rate law, we would say rate equals K times A to the first times B to the first. To figure out the overall order, we would say 1 plus 1 equals 2. So the overall order is 2. Now it doesn't matter what set of data we're going to choose. Let's choose the first set. We're going to plug it into our rate law to solve for K. So we'll say 2.4 times 10 to the negative 6 m over s is equal to K times 0.01 times 0.025. So 2.4 times 10 to the negative 6 m over s is equal to K times 2.5 times 10 to the negative 4 m squared, since I multiplied my concentrations. So I'm going to divide to figure out my K value. And K would equal 0.0096. Now if I look at my units, m is going to cancel one of those m's, and then I have over seconds and over m. So that would be 1 over sm, or you could write that as 0.0096 s to the negative 1, m to the negative 1. If we're given a reaction mechanism, then we can actually determine the rate law simply by looking at the rate determining step. The rate determining step is always the slowest step. You're only as fast as your slowest runner. So they would have to tell you which one is fast and which one is slow. So the slow step, or the rate determining step, happens to be the first one here. So to write the rate law, we'll say rate equals K, and then we're only worried about the reactant, C4H9Br. The coefficient is 1, so it's first order. If the coefficient was 2, then it would be second order, 3, third order, and so on. What's the overall balanced equation for the reaction? So we're going to add all of these reactions together, combine them into one reaction. I have some duplicates though. I have some things that are reactants and products, and so they should cancel out. C4H9 plus cancels because it's a reactant and a product. And then so does C4H9OH2 plus. So then if I combine everything else together, what do I have left as a reactant? C4H9Br, and I have 2 waters. And then as products, what I have left is Br minus, C4H9OH, and H3O plus. Now the intermediate would be something that's not a reactant and not a product. So it's the things that we actually canceled out. So C4H9 plus is not a reactant or a product, so that's an intermediate. And C4H9OH2 plus, again, not a reactant, not a product, so it's an intermediate.